you very much. Thank you very much. I'm going to talk to you about paving the road to Exascale, but the technologies, the capabilities of Mellanox Infiniband that I'm going to discuss with you can accelerate application performance at all scale. Mellanox is proud to be part of the US push to Exascale. We're going to be the interconnect in Oak Ridge National Lab. It's already installed, and this is going to top the next top 500 and probably the last top 500 system before we reach Exascale. After that's done, we are going to be doing a similar thing out in Lawrence Livermore National Lab, building the Sierra system. Mellanox also interconnects the largest supercomputer in Japan, the fastest supercomputer in Canada, which is being built now at the University of Toronto using a novel Dragonfly Plus topology that we've invented. And the largest commercial cluster at British Petroleum is interconnected by Mellanox Infiniband. Now we live in a world of data, and it's growing year after year exponentially, being driven by HPC and cloud, big data analytics, but increasingly by machine learning. Data is becoming a big challenge to store and process. And big data is delivered through the fastest, lowest latency interconnect available, Infiniband, to storage from our partners like DDN. Mellanox makes end-to-end interconnect solutions, from the ConnectX adapters to the switches and the cables that interconnect them. Middle of next year, we're going to be delivering ConnectX 6, the first HDR 200 gigabit per second adapter, and Quantum, the first 200 gigabit per second switch. We also have software that enables the offload capabilities of Infiniband. Now, if you look at the storage market, RDMA is the key technology to deliver the best in storage. Whether you're talking about parallel file systems or even distributed file systems, Infiniband and Ethernet using Rocky can deliver RDMA performance either through iSer, through parallel file systems like Lustre, GPFS, or Ceph. And faster storage like NVMe and persistent memory are going to be challenging the technologies that interconnect nodes, trying to deliver that performance remotely. Offloads like NVMe over fabrics are key to performance with those technologies. Machine learning and deep learning is coming on strong, and fortunately the interconnect technologies that were born and bred in the HPC world apply to machine learning as well, and big data storage analytics. Even though they enable different verticals, they share common needs. So this is probably the most important message that I'm trying to communicate at this show. CPU-centric networks, which are passive participants in computation, a push-me, pull-you architecture where CPUs and GPUs simply send data across to other endpoints, are dying. They cannot keep up because the servers that are running the applications have a competition with the actual processing needed for the network stack. So what Mellanox is trying to do is introduce a new generation of coprocessor within network computing, enabling our network adapters and our switches to perform computation as data is on the fly, performing things like collective operations and MPI tag matching. In this way, we can realize order of magnitude improvement in performance. There are 4 of many different offload capabilities that I'd like to talk to you about. The first one, called SHARP, is an acronym. It stands for Scalable Hierarchical Aggregation and Reduction Protocol. But the important thing is that this enables Mellanox switches to recognize MPI collectives and perform aggregation and reduction operations on the fly. Imagine 18 nodes connected to a switch, all reporting the results of an MPI all reduce. The switch does the all reduce operation and just forwards a single packet, the result of the interim aggregation. If every switch in a fabric can participate in this way, by the time the result gets to the destination process, the root process, all of the computation is done. Instead of 1,000 packets all trying to be jammed through a single port, only a single packet with the answer is delivered to the root process and computation can continue unimpeded. This realizes an order of magnitude performance improvement for applications. On the adapter side, we've implemented MPI tag matching. Now, MPI implementations typically have two different methods of delivering data. For small packets, they use what's called the eager protocol. It's called the eager protocol because a node just sends the data to a remote node. But when you get to larger message sizes, eager is no longer efficient. And most MPI implementations will switch to something called rendezvous, where the message that's sent to the remote node is, I have data for you, please fetch it from me. The problem with rendezvous is that the CPU that sends that message then has to block an application and wait for the data to be retrieved. With Mellanox Infiniband and MPI tag matching, however, that entire transaction can be offloaded to the HCA. And the CPU can continue to process the application, trusting the HCA to complete the rendezvous transaction on its behalf. A third acceleration that I want to tell you about is actually not really an acceleration unless you have a link failure. It's called Shield, and it's a self-healing capability for networks. If a link fails in a 1,000 node cluster, typically a software subnet manager would recompute all of the routes and distribute them to the switches. And even for a high performance subnet manager, that can take a couple of seconds. For a 10,000 node cluster, it might take 10 or even 20 seconds. What Shield does is it teaches the switches how to take action in the event of a link failure. A switch with a link failure that has more than one route to a destination node can simply take the new path using this protocol. And if there is only one path available to the destination node, it understands the topology and in 1 millisecond can tell the switch upstream who has an alternative route to begin using that. This is recovery at the speed of data. So instead of your MPI job failing because many packets are dropped over that 2 to 20 seconds, 1 millisecond recovery means that the computation can proceed unimpeded. And the last capability I want to tell you about, and I hope you already know about, is GPU Direct. GPU Direct is the unique capability of Mellanox HCAs to act as a PCIe busmaster and communicate with GPU memory without any CPU involvement, moving data from GPU to remote GPU with more than 97% reduction in CPU utilization and a 30% improvement in latency. Actually, in the case of larger messages, up to an order of magnitude improvement in latency. But really, the important thing is where the rubber hits the road. What does this mean for application performance? We can show you network latencies and MPI bandwidth as much as we'd like, but what does this mean for applications? Mellanox does testing of applications in many different areas of science and technology. And we just demonstrate 1.5 to 2.5 times better performance than our competition. If you were to normalize Mellanox at 100% efficiency as you scale a fabric, and it is pretty close to that, take a look at the scaling of OmniPath as we get to 64 or 128 nodes for applications such as GROMACS, NAMD, Fluent, LS-DYNA, VASP. Drilling down, for example, into LS-DYNA, a CFD code, which is very communication heavy. You can see how Mellanox Infiniband can deliver higher performance with 16 nodes than a CPU-centric architecture such as OmniPath using 32 nodes. Another way of looking at that is to simply build a cluster that delivers the same performance with the two different fabrics. It doesn't matter if Intel gives away OmniPath for free. The total cost of the cluster, because you need more CPUs to process the network and to make up for the inefficiency in scaling, means that Mellanox delivers a 43% lower TCO. This case is a very interesting one because Intel published numbers for ANSYS, another CFD code, showing that OmniPath delivered 18% better performance than Mellanox Infiniband. Up until this point, everything that Intel had published was simply a ratio. They didn't release any actual performance data. But this time, they actually documented the performance. So we were able to bring this application into our lab and run the test with EDR Infiniband, but using all of the accelerations that I talked to you about, not disabling RDMA and using Sharp. And we doubled the performance that Intel had reported for EDR. Once again, delivering more than a 45% better TCO for a cluster running this ANSYS Fluent application. And finally, I have an example using VASP, a chemistry ab initio code for first principle molecular orbital calculations. Here we show that the improvement over OmniPath grows as clusters grow. With a 17% higher performance at only 4 nodes, it grows to a 71% higher performance as we scale a VASP job across 16 servers. And this translates to a 40% lower TCO for Infiniband. So across the board, the message is if you want the best application efficiency, the best performance, the best productivity from your cluster, from your storage, Mellanox Infiniband is the technology of choice. I invite you to our booth 653. Come see the latest generation of Infiniband, ConnectX-5 and Switch IB2, and the next generation HDR products. And I thank you very much for your attention.